then we can use the convolution property to help us analyze what would be the response, the output, if we are given a particular input, let's say an input x of t, that is also of this, decaying exponential form. Okay? So to use the convolution property, right, we know that the output the Fourier transform of the output is equal to the Fourier transform of h times the Fourier transform of x. Okay. Now we've computed the Fourier transform of this, decaying exponential multiple times. So let me just write the result out. So here, the Fourier transform of h is 1 over a plus j omega, and the Fourier transform of x is 1 over b plus j omega. Okay? All right. So this is, going to appear a lot in some of the homework. So it's good to know, right? So basically, the Fourier transform of this single-sided exponential, right, is just 1 over a, which is the exponent here, right, plus j omega. Okay? So then by the convolution property, we know that yj omega is equal to hj omega times xj omega. Okay? And this is equal to 1 over a plus j omega b plus j omega. Okay. All right, so what I want to show here is to show you how to find the output of this linear time invariant system using this convolution property rather than directly computing the convolution of these two signals. Okay? So we've done this convolution before, and you can, if you recall, it can be a little bit tedious. Okay? But here, if you use the convolution property, right, you know that the output Fourier transform is equal to the product of the Fourier transform of these two, which gives you this. Okay. So the remaining task is just to find the inverse Fourier transform of this to get the actual output signal. Okay. Now let us split this into two cases. Right. Now, first of all, suppose that A is not equal to B. Okay. So for A not equal to B, right, we can factorize this into the sum of two fractions, right, using the partial fraction expansion technique. So we can actually write this as some constant A over A plus J omega plus B over B plus J omega. Okay? So this is a technique called the partial fraction expansion. Okay? So you may have, used this before in your calculus class. Okay? But anyway, right, the way this goes is that, when you have this 1 over the product of these two terms, right, you can split them into a constant over this first term plus another constant times the second term. Okay? So then the question is, what are these constants? Okay. So basically, you can combine the two. If you combine the two, then you will have something that has A plus J omega times B plus J omega in the denominator. And in the numerator, you have A times B plus J omega A plus A times B plus J omega B. Okay? So when you combine these two, right, you have multiplication of these two terms in a denominator, and you have capital A times B plus j omega plus capital B times A plus j omega. Okay? And this thing must be equal to this. So this means that the real part here must be 1, and the imaginary part must be 0. Okay? So A, B plus A, lowercase a, capital B is equal to 1, and capital A is equal to minus B. Okay? Now, if you substitute this inside here, then you have AB minus AA equal to 1, which gives you A equal to 1 over B minus A, which is equal to minus B. Okay. Right, so this is, just how you obtain this, this expansion, right, using the partial fraction expansion approach. Okay? So you take the value of A and B, plug it back inside, right, and you will get, okay, y of j omega equal to 1 over B minus A, 1 over A plus j omega minus 1 over B plus j omega. Okay? Okay. So I'm just plugging this capital A and B inside this expansion here. Okay? And this is what we get. Right. Now, from this formula, you can immediately see why we want to write it in this form. Okay? Because once we write it in this form, then we can directly observe what is the inverse Fourier transform. Okay? Because we know that the inverse Fourier transform of 1 over A plus j omega is the decaying exponential with exponent A, right? So it's the relation between these two, okay? And we know that the inverse Fourier transform of this is a decaying exponential with exponent B, okay? So, by inspection, we get y of t equal to 1 over B minus A, e to the minus at, u of t minus e to the minus bt, u of t. Okay. Now this is when A is not equal to B. Okay, so that these two factors are different. Now, if A is equal to B, then these two factors are the same. So you do it slightly differently. Okay, so in that case, you will have, right, if A is equal to B, then you will have 1 over A plus j omega squared. Okay. So for B equal to A, you have yj omega, that is 1 over A plus j omega squared. Okay. So then how do you find the inverse Fourier transform of this? Okay. So the trick here is that you can observe that this 1 over A plus j omega squared is actually j times the derivative of 1 over A plus j omega. Okay? Because when you take the derivative of this, right, this becomes squared, and you will bring out a minus j outside when multiplied by j becomes 1, okay? So this 1 over a plus j omega squared can be written as j times the derivative of 1 over a plus j omega. Right. So then by the differentiation property, we know that since e to the minus at ut has a Fourier transform that is 1 over a plus j omega, okay? Therefore, when you take the derivative of 1 over a plus j omega, okay, then in the time domain, you should have minus jt times the original time domain signal. Okay? So by differentiation property, we know that this derivative has an inverse Fourier transform that is this, right? So the inverse Fourier transform of y is just j times this. Okay. So hence, y of t is just j times minus jt e to the minus at u of t, which is t e to the minus at u of t.这个是从这个 differentiation property， 所以 differentiation property 就是我们有证明从时间到那个 frequency domain 的，就是如果对，就是我如果对这个 x of t 去微分的话。那么它的 frequency domain 就是这个嘛 ，OK， 那它的这个对称的 relationship 就是 by duality， 你也可以得到反向的 differentiation property，OK， 就是这个，其实就是上面写的，就会是负 j t x of t。OK， 所以这个在上一份的投影片里面。OK 吗 ？Okay. So I went through this example in detail because you're going to encounter this kind of computation in other places as well. Okay, because this type of decaying exponential you will often see in a lot of systems, right? For example, for systems involving RC circuits. Okay. So this type of computation will arise here and there. Okay. So the key is to use this partial fraction expansion. If you're not familiar with this, they have some explanation in the appendix. Okay. So see appendix if you're not, familiar with this. Okay. Any other questions? Okay. So this example is really just to show you that, there's an alternative way for finding the output other than directly computing the convolution. Okay, because computing the convolution, often can be quite tedious, right? So this alternative way is to first convert both of these into the frequency domain, multiplying them together and taking the inverse Fourier transform. Okay. So this is one example, right? If you're not convinced that this is easier, right, we can look at another example. Okay. So in this second example, we have an impulse response that is an ideal low-pass filter, meaning that the time domain response is the sinc function. And suppose that our input is also a sinc function. Okay. So imagine computing the convolution of these two sinc functions, right? This is definitely, going to be quite tedious. Okay. But you can do this easier through the frequency domain. Right. So first of all, we know that for a sinc function, right, the frequency domain is this ideal low-pass filter that is 1 for omega within omega c. And the signal also is 1 for omega within omega I and 0 otherwise. Okay? So the frequency, the Fourier transform of both of these are, ideal square signals in the frequency domain. Okay. So hence, y, the output, okay, will be the multiplication of the two. Okay. So when you multiply the two, right, these are two perfect square signals. So when you multiply the two, you will still get a square signal. It's just that the bandwidth is determined by which one is smaller. Okay? So if omega c is smaller, then you will also get a square wave between minus omega c and omega c. Okay? And if omega I is smaller, then you will get something that is between minus omega I and omega I. Okay. All right, so for this example, you can definitely see that it's easier computing the multiplication in the frequency domain compared to computing convolution in the time domain. Okay? And then taking the inverse Fourier transform is easy, right? Because the square wave has an inverse Fourier transform that is a sinc function. Okay. So therefore, y of t is equal to sine omega ct over pi t if omega c is less than omega I, and sine omega I t over pi t if omega I is less than omega c. okay? So we talked about this convolution property extensively because this is very important for analyzing the input-output relation of a linear time-invariant system, okay? Right, so the convolution property tells us that when you take the convolution of two signals in the time domain, this will correspond to the multiplication of their signals in the frequency domain. Right. Now by duality, right? By duality, you can also flip this around to get what we call, the multiplication property. Okay. So a multiplication property says that now if you instead have the multiplication of two signals in the time domain, then this will correspond to convolution in the frequency domain, okay? Scaled by this 1/2 pi. Okay. Now this is also sometimes called the modulation property because when you multiply, right, when you multiply one signal on the other signal, you're basically modulating the amplitude of this second signal, right, or the other way around, okay? So when you multiply, some signal with the other signal, you're basically modulating the amplitude of this signal, okay? So for example, if P of t is just some sinusoid, right, which originally goes from 1 and minus 1, but if you multiply it with S of t that takes on some shape, then this sinusoid no longer has amplitude 1 and minus 1, but instead has an amplitude that, that varies according to S of t, okay? So this operation is very important in communication systems, right? Because this is how we embed the information that we want to transmit, for example, our voice signal, on top of some cosine or sine carrier that we transmit over the medium, okay? All right, so let's look at an example here, right? So suppose that S of t is this signal, right? You can think of it as, let's say, our voice signal, okay, which has a spectrum, S of j omega, and let P of t be some carrier cosine omega naught t, okay? Now, when you multiply the two together, right, what do you get? Okay. Now, notice that P of t, you can write by Euler's relation as 1/2 e to the j omega naught t plus e to the minus j omega naught t. Okay? So then if you take the Fourier transform of P of t, you get this capital P of j omega that is equal to pi delta omega minus omega naught plus pi delta omega plus omega naught. Okay? So we learned previously that the Fourier transform of a complex sinusoid, right, corresponds to a delta function at that particular frequency, okay? So the Fourier transform of P of t is this capital P of j omega that is a delta function at omega naught plus another delta function at minus omega naught, okay? So then what is the spectrum of R of t? Right. So the spectrum of R of t equal to S of t times P of t is this Rj omega that is equal to the convolution of S j theta and P j omega minus theta d theta. Okay, so this I obtained by just copying this down. Okay, now let's substitute P inside this integral. So this will give me 1 over 2 pi s of j theta pi delta omega minus theta minus omega naught plus pi delta omega minus theta plus omega naught d theta. Okay? So I'm just replacing this p with this formula here. Okay? So this p is at omega minus theta, so I have to plug in omega minus theta into omega here, which gives me this. All right. Now, when you take the convolution, when you take the integral of any function times a delta function at position at omega minus omega naught, then you're basically, moving this signal to the frequency omega minus omega naught. Okay? So when you work out this integral, you will get s of j at omega minus omega naught. And similarly, in the second term, you get s of j of omega plus omega naught. Okay? All right. So then what is this? All right. So what this is basically the spectrum of the signal S, okay? The spectrum of the signal S moved to frequency omega naught, and another copy of the spectrum moved to frequency minus omega naught, okay? Each scaled by 1/2. Okay? Okay. So here is an illustration of what's happening. Okay. So suppose that this is the spectrum, the frequency domain of the signal S. Okay. So you can think of this as your voice signal, right? So the signal for your voice when you talk on the phone. Okay. So when you multiply S, right, in the time domain, when you multiply the voice signal by this cosine function, okay? This cosine function has a Fourier transform that is equal to these two delta functions, one at omega naught and one at minus omega naught. Okay. So when you multiply the signal with the cosine signal, the voice signal with this cosine carrier, what you get in the frequency domain is the convolution between these two, which moves this spectrum up to frequency omega naught and also down to frequency minus omega naught. Okay? So this is very interesting, right? Because your original voice signal is moved to a higher frequency without any loss, right? All of the information contained in your original signal is still there. It's just that you have moved it to a higher frequency. Okay? So you can see that this sort of preserves information but shifts to a higher frequency. Okay. So this is what is typically done in a communication system, right? So if you're talking about wireless communication, then this is what you do in the first couple of generations of your mobile phone, right? So you may speak into your phone, generating this signal S, then it will be multiplied by a carrier that moves it to some center frequency, right, which is at that time maybe around 800 or 900 megahertz. Okay. So the reason you need to move your signal to a higher frequency is because, when you transmit the signal over the air, only certain frequencies have a good, response, right? Or let's say certain frequencies have less distortion when you transmit it over the air. Okay, so if you transmit directly this baseband signal, then it will quickly saturate and quickly decay, and you will not be able to reach very far. Okay, so you usually have to also, modulate it up to a high frequency, a frequency where your channel will have a good response, right? So that the receiver can receive this signal well. Okay. But then how do you extract the information from this high frequency signal here? Okay. So how do you reconstruct this original voice signal back? So the way to do this is actually quite simple. Right? You take this R of t, right, this modulated signal R of t, and you multiply it again by P of t, which is this cosine carrier. Okay. Now what happens here? Right, so suppose that this is R, right? You have a copy of the voice here and a copy of the voice here. Now when you multiply it by P of t, which has a spectrum equal to 2 delta functions, when you multiply it by P of t, then in the frequency domain, it would be the convolution of these two. So when you take the convolution of these two, right, you would be moving this spectrum, okay, up to center frequency omega naught, right? You'll move the center to omega naught, which will move this back to baseband. And this delta function will move this signal down by omega naught, which will move this again to baseband, right? So a copy of this is moved to baseband, which is, aggregated with a copy of this, also moved to baseband. And eventually, this is what you get, right? So you get the aggregate of these two copies here, and then you have one copy moved here, and one copy moved here, okay? All right, so this moves up to minus 2 omega naught, and this is moved up to 2 omega naught, okay? So then we again get something that looks exactly the same as this, right, with a scale of a over 2, but the scale is not a problem, right? We can just multiply it by 2 to get this exact same thing, okay? So the scale just basically corresponds to the amplitude of the signal, right? So how loud this signal is, right? So you can multiply this how many times, however many times you want, okay? If there is no noise, okay? All right. But the problem is that you still have these two signals at high frequency, okay? That may interfere with the original voice signal. So what you need to do further is to pass this signal through an ideal low-pass filter. Okay? So first of all, by multiplying this, you will get here at baseband, a copy that is equal to 1/2 S of j omega. And you will need to extract this out by passing this G through an ideal low-pass filter. Okay, so let's call this H of j omega. Okay. So this is a very typical amplitude modulated communication system. Right? So at the transmitter side, you take the signal S of t, you multiply it by P of t to get the signal R of t, okay? So this is a signal at frequency omega naught, okay? Then at the receiver side, when you receive this R of t, you multiply it by P of t again, pass it through an ideal low-pass filter, and you will get at the output the original signal S of t, just scaled by 1/2, okay? But this scale is usually not a problem because you can just amplify it.